Mountain waves. A mountain wave is not something you do from your aeroplane while flying over backpackers in the Rockies. A mountain wave is something much more interesting. Throw a pebble in a still pond and wave patterns radiate outwardly, eventually traveling across the entire pond. If we move water over a pebble, a curve is added to the flowing stream. When air moves over a larger pebble, a mountain range for example, it also has a curve added to its motion, as shown in Figure 82. Given enough wind speed and large enough mountains, these wave patterns can travel hundreds of miles from their generating source. Very stable air, moving above the level of surface friction, usually flows in a laminar or smooth, layered pattern. But when it encounters a large enough obstacle, a mountain range for example, a standing or mountain wave pattern is established in the mass of moving air. The standing wave is very similar to the wave which appears when a long rope is given a good shake at one end. The wave pattern appears to travel the length of the rope, eventually dissipating in a flip at the end. Mountain waves do something very similar. As wind, usually with a velocity of 40 knots or more, encounters a sufficiently large mountain, a perturbation or shake of the rope occurs. A wave pattern is induced in the once smooth-flowing or laminar air. This pattern sets up a series of waves in the downwind direction, with valleys and peaks that remain stationary. Given enough moisture in the stable air, condensation, from the air cooling as it rises, occurs at the peaks of these waves. Directly over the mountain top, a pileus or cap cloud occurs above the rough mountain surface. That's not Pontius pileus either. Wrong guy, wrong story. Farther downwind, almond or lens-shaped clouds form at the wave crests. These clouds are called lenticular clouds because of their lens shape. As moist air rises on the upwind side of the wave, it cools and condenses, producing a cloud. On the downwind side of each wave crest, the air sinks and warms, resulting in the cloud droplets evaporating. Lenticular clouds differ from other clouds not only in shape, but because they appear not to move. This is because the air is rushing through them as they continually form on their western edges and evaporate on their eastern edges. This is why they are sometimes called standing wave clouds. When the air between the cloud-forming layers is too dry to produce clouds, lenticular clouds will form one above the other. Sometimes, when a strong wind blows perpendicular to a tall mountain range, the wave pattern extends up into the stratosphere. This produces a dramatic display resembling a fleet of UFOs. It's quite typical for mountain waves to form 100 miles or more downstream from the mountain barrier. Directly underneath the lenticular clouds, a small rotor cloud can frequently be found below mountain peak altitudes. Rotor clouds result from the frictional effects of the surface and a lifting action from the rising crest of air. Air velocity is slowed near the surface yet flows faster at higher altitudes. This adds a rolling motion to tubes of air similar to the forward motion of a baker's rolling pin. Long, cigar-shaped clouds form, each containing severe turbulence. These clouds are to be avoided like cooties were avoided in 6th grade. Violent turbulence will also be found in the up and down drafts associated with lenticular clouds.
Pilots must be especially cautious when flying near or around mountain waves. Many varieties of turbulence appear in these wave patterns. Keep in mind that mountain waves can and do form in dry air. The only problem is, you can't see them. In other words, telltale lenticular clouds are not visible. With the lack of clouds in dry, fast-moving air, pilots sometimes expect little or no hazard when approaching a mountain. Smart pilots, however, understand that winds in excess of 25 knots at mountaintop altitudes are sure to bring some degree of turbulence as well as up and downdraft hazards.
Approaching a mountain on the windward side or the upwind side, you might find yourself climbing at several thousand feet per minute with power completely reduced. While this produces one heck of a ride, it's not as dangerous as approaching a mountain from the leeward side or downwind side with insufficient altitude. Approaches to mountains with strong winds present should be made with caution, because the strong downdrafts can easily exceed the ability of a light airplane to climb. One way to minimize the risk if you are uncertain of conditions is to approach the ridge at a 45-degree angle. If downdrafts are encountered, you need only make a 90-degree turn to avoid the mountain instead of a 135-degree turn.
Mountain wave dangers. Hello folks, Rod Machado here. I'd like to talk to you about the dangers associated with mountain wave phenomena and why it's important to understand that we need to use the 45-degree approach strategy when approaching any mountain range above which we suspect that winds are blowing in excess of 20 to 25 knots. Now, take a look at this graphic. This graphic makes the point. The magenta dots represent a few, certainly not all, of the mountain wave accidents that occurred in Southern California. And the dark green and brown areas represent mountain ranges. Look very carefully here because those magenta dots are right on the lee side, right on the downwind side of those peaks. And that should make the case for why we should use caution when approaching a mountain range. Now, I don't want you to walk away from this presentation thinking, oh my gosh, I will never operate over a mountain range. No. That is not the lesson I want you to learn here. What I am saying is to use caution and use a defensive strategy when approaching any mountain range, in particular one where you might not know what the wind velocity is over that range. Therefore, when you approach that range, you approach it at a 45-degree angle. That allows you to turn away from the mountain range through an arc of 90 degrees rather than an arc of 135 degrees, which is what you would experience if you approach that mountain range at a 90-degree angle. It's just a good defensive strategy. Of course, if you can, it's always wise to cross a mountain as high as you can. Sure, it would be nice to cross the mountain as high as we possibly can, but sometimes that's just not a practical strategy. So if you're going to approach the mountain range, approach it at a 45-degree angle and take a look and at least cross at a minimum of 2,000 feet above ground level. And if you know the winds are blowing at 20 to 25 knots, then perhaps you'll even cross it higher while still applying the same 45-degree approach strategy.